Okay. Then I will be the president of the jury. Okay. I'm Vincent from Brest University. Okay. And I will introduce shortly the jury member. Firstly, the reviewer Antonio GASTERATOS, which is a professor in Democratic University of Thrace in Greece. Simon LACROIX, also a reviewer, directeur de recherche, director of research in LAAS in Toulouse. And Tomas SVOBODA, also professor at Czech Technical University in Prague, in Czechia. Okay, thank you. And also Cédric DEMONCEAUX, which is professor at the University of Bourgogne, and Cédric BUCHE, which is close to me, from ENIB and also LACROIX in Australia, and myself from Brest University. Before Panagiotis starts its defense, I will recall you that he will have 45 minutes to present his work, and after, only after, you will have a session with answer and response. You can ask after what you want to the candidate. Okay? Then Panagiotis, you have now 45 minutes.
Just some seconds to set up.
Perhaps you want to...
Sharing of... Can you see my presentation?
Est-ce que tu veux qu'on...
Voilà, reprends le micro.
So can you see my presentation in WebEx? Is it okay?
No.
Okay. Give me a second. Yeah, so I will move this window right here so that I have better control of that. So share. So now it should be okay, I guess?
Yeah.
Okay. Up. And with that, I think I can go. Yes. So good afternoon, everybody, and welcome to my presentation, for my presentation to direct research, which is positioned in the domain of computer vision and robot navigation in a three-dimensional environment. I would like to thank all the members of the jury for making it to this presentation, either online or in present. So to begin my presentation, let me give you a short biography sketch of my research career so far. So I started my PhD in 2005 in the University of Athens, in collaboration with National Center for Scientific Research Democritus. I completed my studies in 2009, and right after I fulfilled my military obligations, national military obligations. And in 2010, I performed my first foreign postdoctoral stay in the University of Rome, La Sapienza, until 2012. And in 2012, I moved to France. I joined a technology transfer project of INRIA between two INRIA centers, INRIA Grenoble and the INRIA Sofia Antipolis. And finally, I performed the last academic stay in Paris in 2016, mid-2016. Mid-2014 until 2016. And from that date forward, I have been an associate professor in INT Atlantique, Brittany, Pays de la Loire. So my HDR covers a period of almost 12 years, which is possible to condense in a presentation of 45 minutes. To complete my self-presentation, let me give you some indicators of results that I have attained throughout the years, especially in terms of research. So I have a total of 42 international peer-reviewed publications. Almost 1 out of 4 is in top-tier journals or venues. In Scopus database, you see some statistics on the right. In terms of citations, I have supervised PhD students, postdoctoral researchers, and master students. Currently, I am supervising 6 doctoral students, 2 postdoctoral researchers. In terms of the responsibilities, CNRS. The group is called the Rambo. I have also been appointed reviewer of doctorate thesis, as well as master thesis, and I have also gained grants as principal investigator that total almost a little bit less than 1 million euros. In terms of teaching, I have performed around 900 hours in French institutions, but also abroad. And to summarize my journal publications, you see the graph on the bottom right. You see the journals ordered with respect to the impact factor in the green, in the red bar, and the green bar, the corresponding number of articles per journal. So with that, I will conclude the self-presentation of what I have accomplished. Now for the sequel, I will structure my presentation following the schema of my dissertation, of my manuscript, but it will be a subset of what I have included. So first I will start speaking about computer vision in three-dimensional environments, followed by the two parts that you see. So speaking of computer vision in three-dimensional environments, most of the time this concerns the resolution of inverse problems. That is, problems where we have in our disposal a collection of data, of observations, and we try to devise the underlying rules, causes, or models that generated this data. There are also forward problems involved, but to a lesser extent. And so in terms of applications, I started to work in computer vision for digital libraries of three-dimensional objects. And right after the completion of my thesis, I expanded my horizons to autonomous robots and autonomous robotic vehicles. Now, this constitutes, in my regard, a domain change or a domain enlargement for different reasons, but most importantly, due to the fact of different concepts and different disciplines that have to be used. So speaking of digital libraries, this mostly concerns closed set problems. That is, problems where the data, as well as the models that have generated this data, are closed and do not change over time. On the other hand, when we start to be interested in robots that are out of a cage, out of an industrial environment, such as robotic vehicles, then by default we are interested in open set problems. And in these kind of situations, the data, as well as the models, change over time. They are not constant. And in fact, they become larger and larger. So this requires a different mindset to address this kind of problems. Now, during the years, since, as I said, I started with digital libraries and then I started to explore autonomous vehicles, the progression was not completely linear. It was not straightforward. But in a few lines, or in a few, let's say, if I could wrap up my progression in terms of disciplines and methodological approaches, I started to use shallow learning techniques and model-based approaches, followed by deep learning and, more globally speaking, framing the problems to address as incremental learning problems and meta-learning problems. So my narrative for the sequel will be as you see on the right. So I will start speaking about contributions in 3D vision concerning closed set problems, constrained environments, static environments, digital libraries, and at the very end I will conclude with dynamic open set problems, dynamic environments. So the first topic that I would like to speak of concerns something that I addressed during my thesis, but I didn't have the time to conclude due to time constraints. And this was the problem of shape normalization of three-dimensional objects. So this is a step that has to be performed so as to not account for the similarity transformations that undergo three-dimensional objects. So here you see on the right a certain object that can have an arbitrary pose, scale, rotation, translation. This should be done for articulated objects, but also for rigid objects. But it turns out that minor deformations or minor changes in the shape, such as in the two qualitative examples you see in the middle, can have a dramatic impact in the shape normalization. So, for example, in the calculation of the bounding cube or the center of mass. So what I proposed here was to learn a sign distance function, a robust sign distance function that would be able to classify a 3D mesh into its core three-dimensional object, the central part, and the non-core three-dimensional object that is subject to the deformations. So if that would be possible, then we would be able to normalize using the robust sign distance fraction instead of the original mesh. There could be different ways to do that. One approach that I explored was the one-class support vector machines that had mainly two tunable parameters, the gamma and the V that you see on the top right. The first controls the level of resolution by which we can represent the 3D object, but the most important is the second one, the V parameter, that controls to what extent and what degree we can take into account the core three-dimensional object and discard all the rest. In the middle, you see qualitative examples of this approach being employed. So a comparison between the proposed approach and the standard approach, and you can probably notice the better correspondence between similar 3D objects using the proposed approach. That was also evaluated quantitatively in terms of performance gains in 3D object retrieval. And I would like to note that this was work that was performed as part-time. It was not financed by a particular project, but nevertheless, it was possible to have a good publication in the respective field. The second topic that I would like to speak in this chapter concerns the perception of objects in noisy RGBD data, so color data and depth data. Now, aside the obvious differences in domains between depth images and RGB images, you see an example in the very beginning, there are also considerations to do with respect to the way by which a robot inspects an object from different viewpoints. So here on the middle and on the right, you see on the same column the same object seen from different viewpoints, and depending on the viewpoint, it can be perceived as belonging to a completely different class. So for example, in the middle, in the top, it would seem like a book. In the bottom, it would seem like a laptop, even if it is exactly the same three-dimensional shape. So here there are considerations to do as how to fuse, how to aggregate conflicting hypotheses. And so for all these questions, I propose an early fusion scheme, an early fusion approach termed PLDI. I will explain later what it is. And the late fusion scheme to evaluate the different aggregation schemes of labels. So let me give you some more details about these two contributions. With respect to the first contribution, the early fusion, this amounted in a few words in the application of an iterative joint bilateral filter that operated in depth, color, and the spatial domain. So this, as I said, is applied iteratively, so as from the one hand to smooth the depth image, but also to reconstruct missing parts. So once this filter gets terminated, then from the four channel images, we arrive to a single channel image that is able to quantify depth, photometric characteristics, but also surface orientation characteristics, due to the fact that to produce this PLDI image, we use internal camera parameters to cast rays inside the scene and compute the intersection of these rays with the surface orientation. I will give you some qualitative examples now with respect to the reconstruction of the scene. So here you see this approach operate as it would operate in these particular examples, and you see how it is able to reconstruct the scene through this application of the filter. This was quantitatively evaluated in a custom-made dataset that I generated in an indoor environment. This was on the left, and on the right, it was also quantitatively compared to a public dataset, the ModelNet 10 dataset, and it was found superior in terms of precision and recall in relative terms, that is, when we account for the dimensionality of the final description. And I have circled here with red the dimensionality of that descriptor, so it was about half the dimension of a seed feature point, so it was particularly discriminative. And with respect to the late fusion scheme, the way that I addressed it is to cast this problem as a hidden Markov model of first degree. This was done by using as an observation the PLDI feature vector that I explained just before. For the state, it quantified the category of the object, but also the rotation, the viewpoint by which it was observed. And for the transition probability, there we could use knowledge about the robot motion. The robot motion model is a simple conditional probability that is rudimentary to have when we know robot odometry. But in the case where we don't have access to that, or in the case where we cannot assume that the object remains static between the different viewpoints, there can be different variants of this hidden Markov model. that give rise to different aggregation schemes that I evaluated. Here you see a snapshot of a table of that comparison. So this was evaluated in a model net 10 dataset as a function of the number of observations that are assembled around an object. There wasn't a particular approach that was proposed here, but more like insights as of that indicated how different possibilities of aggregating multiple hypotheses about a single object. A video demonstration of this approach. So here you see the application of both the early fusion scheme as well as the late fusion scheme. So on the left-hand side is just the object that is in the foreground of the robot, and on the right-hand side is the point of view in color images. You see the objects that are mapped, also classified, and the class that is appointed is the result of the aggregation of the multiple hypotheses that are assembled during a robot exploration. So we change topic. Now I will speak of semantic analysis of three-dimensional scenes. And semantic analysis implies segmentation and classification for the modality of 3D point clouds that can be potentially colored. Now there are particularities here to take into account, notably the intense noise levels compared to conventional images, the complexity of annotation of such kind of data. You can imagine that one has to we cannot click every particular point of the 3D point cloud, but somehow we need to find a way to annotate this kind of data. This has as a result the lack of training data and so forth. And just to give you an idea of these differences, I'm showing you three different examples, three different ways by which we can have a 3D point cloud. So firstly, a point cloud generated by stereo triangulation, secondly from a 3D lidar, etc. So these differences, these different modalities by which we can have a 3D point cloud, bring together with them different levels of noise, different densities of 3D point clouds, and last but not least, depending on the task that we want to solve, which can be a navigation task, which can be a computer vision task, we can have different representations that create a very big arena of possibilities. So here I would summarize the contributions of my works to the PhD thesis of Romain Terzola, who is a PhD student that I have been supervising now for 3 years. His contribution is mainly two things. Firstly, the possibility to artificially generate data, training data, and in particular to use uncolored, unlabeled 3D point clouds to learn deep neural networks to artificially color this kind of data, and to use this as a means for having more data in our disposal. So I mix the two. So so this was the first point, and the second is to be able to generate more realistic data in terms of layout. So to generate three-dimensional scenes where the objects are not randomly placed inside the scene, but they follow some simple rules. And the final point is to be able to put artificial lasers or artificial scanners in places that are more informative. Let me give you two qualitative examples here. So if we focus on the example on the left, you see the ground truth segmentation of an indoor scene. So in different colors you see the different classes. In the right-hand side you see the segmentation of that scene by just using colorless training data. And in the middle there, you see the segmentation that benefits from these artificially colored 3D point clouds. Still in the same topic of semantic understanding, there were other individual, perhaps of minor importance, contributions for the detection of passages, such as doors, staircases, or what we call negative obstacles, which are gaps or voids. And here as well, there were different data sources to be used, such as metric maps, 3D point clouds, but most importantly, trajectories of collocated humans. So I will not speak in depth for all of those. I will just show you a video demonstration of the third one, which consisted in the creation of probabilistic graphical models for that allow to fuse static map queues and human queues. So here you see this work into play. There is a robot that explores an environment, humans that intercept its trajectory. So the robot employs a probabilistic graphical model to detect doors, to point them to the metrical map of the occupancy map of the robot. And it is doing so just relying on the human trajectory and the metrical map. It does not account whatsoever for the visual characteristics of the doors or of the passages. And this has the obvious advantage that we could deploy this kind of robot in any kind of indoor environment. It would suffice to observe a human entering and exiting environments without having to know that the door needs to have a handle or needs to have a specific color or whatever. So the robot uses the human as a roving sensor, actually. The fourth topic, still in computer vision in three-dimensional environments, concerns the perception of human interactions and human dynamics. So now we are more explicitly in applications where we have the dynamics and problems which are more qualified as open set problems. There are two questions here to account. The first is how to represent a single human in robot workspace. And once we are able to answer that, the next subsequent question is how to represent groups of interactive humans. If we are able to do that, then the robot will have a synergistic behavior with the human. Otherwise, everybody will be independent of one another, and this will create conflict, and the human and the robot will not be complementary to each other. So for the question of how to represent a single human in robot workspace, you can focus on the left. So I propose to employ non-stationary skew normal probability density functions, which is a way to express in the mind of the robot, if I can call it like that, the four dominant spacing models of humans. So there have been sociology studies in several decades that have measured that every human maintains around him or around her invisible but real zones of social sensitivity of different levels. And these invisible zones are indicators of the intention of somebody to engage or to avoid an interaction. There are 3 or 4, starting from intimate level, personal level, public level, and this can be measured metrically, let's say. And so the form of these invisible social zones change depending on one's intention. And it can be measured, for example, with respect to the posture, if the posture is closed or open, by different cues of the human skeleton. So this is the first question, the contribution to the first question, and the contribution to the second question amounted in aggregating individually appointed social sensitivity functions so as to calculate a global potential field, a global function of social sensitivity, by casting it as a one-class density estimation problem. So here you see on the rightmost side how it seems like in a simulated, in a virtual environment. So these two works were published in 2013 and 2014 in the IEEE IROS conference in robotics. And the last topic that I would like to speak with respect to computer vision is on human classification, human action classification, in the form of motion capture sequences. So motion capture sequences are trajectories of human skeletons that can be captured with different sensors. There are different challenges to account for, such as interclass variation. So a certain individual or for a certain class of activity, the way by which we can accomplish the same thing can vary considerably. There is an ambiguity with respect to the separation of activities, but it can also happen that we do multiple activities at the same time. And the application goal of this research was to endow a robot or a smart environment to have a better situational awareness of the dynamics associated to humans, and on that basis propose different services. Now, here I would highlight 2 main contributions. So, a preliminary work that was done when I was in Rome. It was Vasamis Duskos and his master thesis that I co-supervised. In a few words, he proposed a shallow learning approach, so a Gaussian process-based Latin variable model to represent human actions. And more recently, the postdoc of Maxime Devan, who was the first postdoctoral researcher that I co-supervised. And since our interest was in activities that were more compound, we explored the use of hierarchical long-term memory networks. So this was in particular for activities of daily living. And with that, I conclude the first part of my talk, so all about computer vision, three-dimensional environments. And now I will shift to the second part of related to robot navigation. Now I think that by definition, when we develop things for robots that are not inside a factory, I think by default we treat open set problems. But with respect to computer vision, there's a better balance between forward problems and inverse problems. The applications that I was interested in started immediately after my thesis, so I started working in urban search and rescue robots, and then progressively I expanded the applications of my interest to assistive and service robots. There are cases quite often where the roboticist tries to create new problems that didn't exist. So we have, I consider myself a roboticist, so I can say that we have dreams. We believe that we can create a system that will be able to satisfy societal need. In this respect, I think there is an analogy to do, for example, with people that wanted to fly. Okay, they didn't have a system to start. They had to do a lot of prototyping. They had to fail a lot. And so this is a particular characteristic of robotics that needs to be taken into account. There's a lot of overhead with respect to infrastructure, experiments, legislation issues, and very importantly, considerably higher workforce and people with whom one needs to collaborate. So a roboticist cannot be alone doing research. Okay, exceptionally it can happen, but it will not be too much technologically mature. So I just want to make a note in that respect, with respect to robotics. And with respect to progression, it is, as I already mentioned, so starting with search and rescue robots and expanding with assistive and service robots. The methodological progression also applies here as with computer vision. So I started working with shallow learning techniques and model-based approaches, which slowly were upgraded to deep learning and incremental learning or meta-learning problem statements. And in terms of presentation, I will start speaking about atypical, dangerous three-dimensional environments, so search and rescue environments. And at the end of my talk, I will finish with dynamic, populated, and more user-friendly environments, human-friendly environments. Now the first topic, so since I was a newcomer in robotics and I considered that I performed a domain change, I needed to acclimatize myself with several different things. In particular, in this study I noticed that there was a lack of systematic presentation of the problem of traversability analysis of unmanned ground vehicles. So simply said, the problem that the robot has to address when it has to decide whether to go over a particular three-dimensional terrain, and not just to take a binary decision, but also when it will decide to go over that three-dimensional terrain, to find a way to do this in an optimal fashion. The objective is to do what? Is to build a function that will map observations of the robot to the actions of the robot. And the form of that function can vary considerably depending on what we have in our disposal or how we frame our problem. So first of all, it's very likely that we will be using, we will be needing a three-dimensional robot model, for example, to do collision detection. When a robot has to decide if it can go to a certain area, in simulation, it will assess if it will be in collision with that obstacle, if it will hurt itself. And obviously, depending on the locomotion, depending on the degrees of freedom, depending on the form of that robot, that operation of collision detection can be very complex to do and prohibitive to do it online. Then the terrain itself can come in different representations, or in the form of a point cloud, of a polygon mesh, or whatever, depending on the sensors of the robot. Thirdly, we may or we may not have in our disposal a precise kinematic model of the robot. And fourthly, depending on the behavior that we want to develop, we may take into account the history of the states of the robot. And last but not least, we have to decide what we are going to optimize. Obviously, the safety of the robot is of primary concern, but once we can guarantee safety of the robot, then we start to be interested to other secondary criteria, such as, for example, traction, perceptual coverage, or ground clearance. And from that point forward, when we start to combine criteria, then they can be conflicting with one another. And this can be scientifically challenging to not to compromise certain of these criteria. So my first contribution here was to perform a state-of-the-art survey, which consisted in studying works from a period of time spanning around 30 years. So I investigated works for search and rescue, for Earth exploration, even to planetary exploration. But this allowed to do a cartography of the field, to identify categories, to identify subcategories, and see the different challenges and different problems that were encountered in each group. But it also allowed to foresee and to map where there was space to do research and innovation. So here on the Venn diagram on the right, you see the works cited in the survey and grouped with respect to which dimensions of the G function were taken into account. And as you see, there were a lot in one particular group, considerably less in another group. So this gave me indications and directions to do subsequent research. Now, this was a single author work in the Journal of Engineering Applications of Artificial Intelligence. It was very hard to do, but it paid off because nowadays it is my most cited publication. So once I have done this state-of-the-art survey, I, together with my colleague at the time, Arnab Sinha, we addressed the problem of assessment of traversability of gaps, that is of negative obstacles for articulated tracked robots. Now, we can identify two sub-questions here. So first of all, what is a gap? It is something which is not explicit. It can be implicitly discovered. It can be generated by different causes. And even if we find a consensus about what is a gap in the navigation of the robot, then the most difficult question is how a robot can go over that gap in a safe manner. And obviously, failure is not an option. So here, we proposed a signal processing pipeline, straightforward signal processing pipeline to deal with this problem, which consisted in a few steps in taking a subset of the 3D point cloud of the robot, then projecting it in 2D polar space so as to account in differences in 3D point density in Euclidean space, which is not transmitted in the polar space. Then a form of clustering, extraction of contours for candidate gaps. And finally, I managed to employ a technique that I developed in my thesis, the normal principal component analysis, which basically gave an initial waypoint to traverse the gap and then final waypoints to go over it. Some qualitative examples of the application of this approach. So this was tested in a simulated car accident scenario during the time that I was in Italy, in Rome. Here you see photos of that scenario on the left and on the right, snapshots of the situational awareness of the robot, and in particular of the three-dimensional point cloud, together with gaps that are detected in the vicinity. You see their contours, and if it is traversable, the corresponding indicated directions as to safely traverse the gap. We change topic, we move on to another topic, that of traversability learning. Now, as I said, the calculation of the collision of the robot with a three-dimensional terrain patch is a very costly operation that has to be calculated numerous times online. So to tackle this problem, I suggested to you to calculate this operation offline and learn a function that would be able to regress it online. And if that would be possible, then we would be able to use this learned function as a heuristic, and we could plug it in to conventional graph search algorithms such as A*. Let me give you an idea of how this worked. So the idea was to take a given robot platform, okay, a tracked robot, with a certain pose of roll, pitch, and yaw, and altitude, to feed it, to let it superpose, to let it settle on top of a 3D terrain patch. Settling means that we let it fall until linear and angular velocity becomes 0. At this point, the flippers go down so as to secure this pose. And finally, in this stable pose, we can calculate whatever stability or traversability criterion we wish. And doing that exhaustively for numerous examples, numerous combinations of the pose of the robot, but also of the 3D terrain patch, we can gather statistics that would allow us, for example, to do a Gaussian process-based regression of the traversability of the robot as a function of the terrain. So I'm changing topic and to a more recent topic that I addressed, the problem of developing controllers for articulated tracked robot manipulators that would allow a robot to go over and down staircases. There are multiple challenges, so this is an understudied problem in the corresponding field due to different factors, due to the danger of performance at the task, due to the, for example, elevated cost of such platforms. So we had a lack of training data to tackle that problem. There's a high dimensionality that is associated to it due to the multiple degrees of freedom of the robot, because there are the flippers, but there is also the arm that has to move or carry an object, and so forth. So the summary of this contribution is concentrates in the PhD of Andrei Mikhyakov, who was the first PhD student that I supervised, who defended in 2022. Basically, he casted that problem as a reinforcement learning-based problem, solved in simulation through an incremental approach. And finally, by transferring these behaviors, these controllers learned with simulation to the real robot, trying to minimize retraining or the transfer. Now, this was done, as I said, progressively, so starting with simple models, geometric models of the robot, as you see on the left, so using wheels instead of tracks, exploring rewards, positive rewards that could solve this problem, then evaluating the convergence of these rewards. Then once this primary objective was accomplished, the next step was to tackle the full-scale problem of going up and down a staircase by also using the arm to control the equilibrium, and using the exact geometric three-dimensional model of the real robot, reassessing the appropriateness and the adequacy of the positive and the negative rewards, and finally transferring these behaviors to the real robot. So the real robot was able to traverse the staircases that it had never encountered in real life. It used the behavior that was learned in simulation so as to accomplish this task in reality. There were different publications that were possible through that work. And aside the scientific contributions, there was also an open source framework that was made available that allowed to learn this kind of behaviors if one downloads this framework, but also to learn it by employing what we call incremental domain randomization. This means that the robot starts to learn with easy environments in using reinforcement learning. Once the reward increases, then the environment becomes more complex, harder. Then it learns new things, and at the end, it is presented with a most difficult environment. So this is what we call incremental domain randomization. The fourth topic, the fifth topic and final topic in robot navigation concerns socially compliant navigation. That is, when we have a robot that has to operate alongside humans. There is obviously the concern of safety, but as I said, once this can be ensured, the secondary goal is to have behaviors that are intelligible, that are understood by the humans. So this builds upon the contributions that I stated earlier on in the previous part, where I spoke about the estimation of this global potential field that quantifies social sensitivity. And this global dynamic potential field could be used as a dynamic occupancy map, allowing the robots to plan paths from a point A, point of departure, to a point B, point of arrival, by using these different ISO levels of social sensitivity. So the idea was to first attempt to find a path in the outermost social sensibility, so to avoid to maximally disturb the interaction. If that was not possible, then to downgrade to the next immediate social sensitivity level, the personal, and so forth, until a good path could be found. So that concludes the part about robot navigation in three-dimensional environments. And I will now shift to the last part, where I will speak about some indicative works of transversal and transdisciplinary work. So the first concerns my role during my first postdoc in Italy in representing the Department of Computer Control and Management Engineering in the context of an FP7 European project. So during this 2-year stay, I had the chance to, and also the duty to work with different research groups to interface with different disciplines. This is just an indicative example of work where different colleagues are present. I could also speak about the period when I was in India, where I was tasked with ensuring a technology transfer between Indria Grenoble and Indria Sofia Antipolis for robot navigation. But the most notable example that I would like to speak of is the urban search and rescue mission in Italy in 2012. So in 2012, in springtime, there were major earthquakes that hit northern Italy, in particular the Emilia-Romagna, Italy. There were entire city blocks that were devastated and villages. And so since we were working in this kind of project at the time, we decided to form a group of researchers of the consortium to go there together with ground robots and aerial robots and perform a mission of humans and robots and rescuers, which was the first of its kind in European soil. So I was the UGV pilot of the robot. This consisted in doing a series of experiments and explorations during 1 week of stay in one part of the devastated area. This allowed to visit, in particular, 2 churches that were devastated, to enter with a ground robot and the aerial robot to navigate, to reconstruct the environment and so forth. As I said, since it was the first kind of mission, the first mission of this kind in Europe soil, it echoed significantly in international media. So, for example, in IEEE Spectrum, in the European Commission newsletter, Italia Fire Brigade, up to the Swiss radio. So I'm particularly proud of my implication and my contribution to this endeavor. And with that, I would like to finalize my talk. There's just one last thing that I haven't spoke of yet. And this is my ongoing and future research. So there are mainly 3 axes of future research that I'm focusing on. The first is meta-learning. As I said, since I work more and more in open-set problems, by definition, these problems are framed as open-set problems, and they require more general-purpose AI and robust artificial intelligence. Now, there are multiple sub-themes that we can work when we speak about meta-learning. I'm particularly interested in incremental learning and transfer learning or domain adaptation. So as when an agent, when a system, when a robot learns something in one particular setting, it will be possible to exploit this knowledge and this behavior to another slightly different environment with minimal effort. There are ongoing projects or a project proposal that has been recently done in this axis, and I qualify this axis more like of fundamental research. The second axis is about simultaneous localization and mapping and navigation. Here the ultimate objective, I think, is to have more synergy between data-driven deep learning approaches and model-based approaches. There is no single paradigm that is performing the best in all possible situations. On the other hand, the synergy works that are investing in synergy manage to go beyond current limits. Some things that I'm interested in here is the synergy with planning, between planning and end-to-end navigation, the possibility to transfer behaviors from simulation to reality. Can speak of zero-shot, few-shot perception or navigation. Here as well, there are projects that are ongoing that investigate these themes. And the third axis is more like an applied research theme. This is the digital twin problems revolving around the notion of digital twin, which speaks of the connection of the real and the digital in a bidirectional way. Okay, we could speak endlessly about what is the digital twin. The main idea is to have a tool, a digital tool, that is able to represent to a high degree of fidelity something which is real. It can be human, or it can be natural, or it can be artificial, it can be a robot. And to use this tool, this digital tool, as a means, for example, to do anomaly detection, to perform experiments, do simulations, or to generate data that would be expensive or prohibited to do with a real agent, with a real asset, let's say. So there are some results that have been attained. I'm just having this slide to show that these are projects that are ongoing, and there are results that are coming out, publications that have been done or about to be presented, some articles that have been submitted are under evaluation, several PhDs that are about to defend this year or the next year. So this has a very good inertia and very good. Last but not least, the robots that have been using throughout the years to do this kind of works. So that's all. Thank you for your attention. That completes my talk, and I would be very happy to answer the questions of the jury.
Thank you, Papadakis. Then now we'll have a question session, and we'll first take a comment session with Antonios GASTERATOS.
Okay. Thank you, Panagiotis, for this very informative presentation. I was lucky that I had already written the written assessment, and also due to the fact that I have also get involved in PhD assessment all these years, and several conferences that I have also attended some talks, for example, the social navigation one in IROS that I had the opportunity to watch live your presentation there and to discuss it. And that gave me also, I had the opportunity to say that it gave me the inspiration to get involved in that area too. It was very, very easy for me to follow both your thesis and today's presentation. I think that you have made a very nice endeavor to integrate all these things that you have made in such a big span of years in a very nice and very seamless way. It is true that if you watch back, any of us, if would watch back his as a bright researcher, you have get involved in many different teams, research teams. You managed today presenting us a homogeneous work, and I want to congratulate you about that.
Thank you.
Having said all this, in my report, I have already provided a question, and let me start with that. I suppose that you are already aware of it, and you have prepared your answer. But I want to elaborate that you elaborate a little bit on this digital twin matter that you described in a recent work of yours, and I want that you would elaborate a little bit on the overall figure.
Yeah.
According to my
Yes.
the question written already by me.
Yes. Can you hear me? Am I heard?
And another remark is that you should speak closer to the microphone, because when to the right, we cannot hear you anymore. So if possible, be as close to the microphone as possible. Thanks.
Yes.
Smartphone connected.
Can you hear me, Antonios? Hello?
Okay.
Yes, it's good?
Okay.
Yes. So the question that you asked me in your report is something of which I didn't speak of today, because I consider that it was of minor, let's say, significance, but happily I will answer to you. So your question was, in that project concerning the construction of a digital twin for a mobile robot that navigated indoors, you made a question about how safety was ensured. So when you try to do something with the digital twin and you try to see how it works in practice, how can you ensure safety? Well, my answer to that is that this project was investigating things even before speaking about safety. So it was let's say a seed project, and the idea was to see to what extent we can use already, let's say, models, for example, in a robot operating system or for SLAM or whatever, to recreate the world of a robot, to ask it to navigate in a particular place in simulation, and see if in reality, to what extent in reality it would do the same thing, and to what extent, if I speak of navigation, means that, okay, we ask the robot to start from a point A, to follow a path to go to another point B, like 4 meters ahead, following a particular path, and then asking the same robot to do this in reality. So safety was not ensured, I have to say this, because there were a lot of parameters to control and to check. So this work was mostly about how can we evaluate the quality of a digital twin? To what criteria can we use to say that the digital twin of this robot is good for this task? And for that particular problem of robot navigation that I spoke, it consisted, for example, in evaluating the correspondence between the paths of the robot, the time taken for the robots to go in simulation from a point, and the time taken for the real robot to do exactly the same path. So it was, we were investigating aspects a little bit before, let's say, strictly considering safety.
Okay. Yes, I understand that it is rather peripheral to your research, after also that you have clearly said today your research goals for the future. Overall, I don't have any questions, because I quite satisfied. I am very satisfied with your thesis and your presentation. My only concern about this, how you plan to involve as a mature researcher from now on. I am also satisfied with the presentation of that part today. And if you want that you elaborate a little further, free on that topic, I will
Yes.
Be happy to hear your plans.
Yeah, so I have already sketched the disciplines and the themes in which I would like to work in the following years. I would like to note that I'm particularly careful not to project myself too far in the future because there are things that come into the surface. I mean, research evolutions that are coming almost every day, I would say. So in that sense, I wouldn't like to project myself too far with respect to, or too much further compared to the scientific disciplines. Then I hope that I will have the chance to discuss what I presented today with my colleagues inside the team. As I said, since I am very much invested in robotics, but I cannot do as an individual research in robotics. I need to see together with my colleagues which particular directions we would like to work in the following years. Definitely, we have a history and we have a dynamic and a strong inertia to work in assistive robotics. So for companion robots that work together with people. Personally, I'm interested to work a little bit more in search and rescue robotics. This is something that I started to work in 2010, but since my leave from the University of Rome, I somehow stopped working in this field. There are some ongoing projects where I restart this area, and I think this can bring some fruits. So I don't know if I managed to answer your question, or you want me to elaborate more in a particular way.
It's okay. I'm okay.
Okay.
We'll pass the floor to the next.
Okay, thank you, Adonios. Thank you very much for your comments and constructive feedback.
You're welcome.
Thank you. Now, we'll have the question of Simon LACROIX.
Simon, it's your turn.
Yes, I'm here.
Yeah.
Okay, it's my turn, right?
Yes.
Okay, great. Thank you, Panagiotis, for inviting me, because it's been a pleasure to read you, and it's been a much bigger pleasure to listen to you. So I will start with just a few comments, which basically say what I wrote in my short report. I don't read this report since I wrote it, like 2 months ago, but I will still make some comments that came up to my mind when listening to you. So first, there's no doubt that you're very active scientist, very dynamic, creative, and for me, you're like an entrepreneur. It's an interesting journey. And of course, this takes into account the fact that your spectrum is quite large. But nevertheless, you will not disperse, because I think you have a goal, you have an aim, which is to make robots work. And as such, you are definitely in an excellent robot state. So it's not just making things work in a kind of manner, but it's resulting to the latest theoretical developments, contributing to them, and integrating them on board robots. So this is what I like in your profile. You're definitely an excellent robot state. The presentation was extremely nice. You mentioned 2 or 3 times the narrative of the topic on 3D computer vision I was almost like you when I was your age. At the time, I became kind of crazy because I had too many things to do on the shifting, switching context 20 times a day. You may lose a bit of efficiency. So in the class, you're not discussion. You're not short of projects, you're not short of students. I think now you have, say, the ability to choose what you will work on and not accept any accreditation. That's on the back. On the regret, my regret is, you remember you applied to CNRS? That was like 7 years ago. And my regret is really to get back because if you had passed, you would have been in that class. And that would have been very sad to have the lab. But good for that sake, good for you, because you're doing very well. So that's it. And now for a few questions. I have 4, but they are short. The first point, the work you made, one of your early work, I could say, on shape sculpture, more than 10 years ago now. How can you reinterpret this work? Is it useful nowadays after the tsunami of deep learning processes, even to the contrast? Do you think this work has still some value?
Yes.
Or do you think it's now obsolete?
Yes. In some terms, it is obviously obsolete. I mean, it became in some sense obsolete while waiting for publications to be accepted. It took for some publications more than 1 year to wait for the journal to make its decision. So that was, we can imagine the degree of obsoleteness like 12 years after that. But other aspects are still, I would say, useful today. So I spoke of the capacity of recognizing shapes by normalizing for the pose. I think nowadays the interest is in neural networks that are called equivariant. So these are networks that are robust to the rotations or to transformations, let's say, Euclidean transformations that happen to three-dimensional shapes. Nowadays we are not interested to normalize for a three-dimensional shape. We have the computation power we have a brute computation power to do this kind of calculations. So as a contribution of my thesis, nowadays perhaps it is less of use, but in terms of challenge and in terms of problem, that is to have methods that recognize shapes independently of the pose, this is, I think, also today relevant. I haven't done works in this respect, but perhaps I will have the chance to do so with some ongoing project or a subsequent one. So, yeah. So that's my
I was not aware of this kind of neural network, which you call equivalent.
Yeah. Yeah.
In which you become independent on some rotation or this kind of thing. So it changes a little bit the landscape. I think in the image-based recognition, you do data rotation, such as applying rotation, which always seems a little bit silly to me. So does this mean you don't have to, I mean, these kind of data rotation are useless with such network, right?
Well, yeah, we can do this for, let's say, for images, but again, this will be, if we take a single image, it will not be representative of all the different facets of the object. So we would need to do that for all possible sides of the object, and obviously this has certain overhead. So yeah, it depends on the availability of computing power and what are the compromises that we can do. If we can be exhaustive and have all the training data at our disposal, yes, why not? Otherwise, I think we could do with less data that are better, let's say, fitted or better understood by the neural network.
Okay. Second question on the slide, and then I will have 2 more on your perspective.
Yeah.
I like very much the video you showed, slide 18, in which you do sometimes I don't think you need to replace it, but the way to detect door is by observing, analyzing the human motion.
Yeah.
This is very interesting to me. It reminds me the concept of absorbance. If you know what it means, so basically when you see an object like a door handle, you know that the door handle would open the door. Here you see kind of infer affordances by the motion of humans. On the way you take the door at the entrance of the stairs, which is strictly speaking, maybe not the door with the handle that timer, but nevertheless it has the semantics of the door because it plays through which you don't know. So I find it very original, interesting, and could be maybe extended to in schemes of learning by demonstration schemes in which you just see what humans do and you infer things from what they do. Do you have ideas of how we could extend this idea beyond the notion of door?
Yeah, so this was it's a good question. I had how to say I had wished to go a little bit further in this work. So in particular, what I showed in that video was to use this kind of human trajectory affordance of detailed passages, but here we have a single individual. The work that I wanted to have done, but I didn't further pursue, would be to infer affordances from groups of humans. So by observing humans doing something, for example, about to discuss or about to have a dinner or about to move something, then to infer affordances for other kind of objects or other kind of entities in the environment. Other possibilities. The difficulty in doing this kind of research is that it's quite complicated to have a ground truth. Okay, so once we speak about human interactions and human activities, the annotation is not so it's not black or white, and it's not always objective. So there is I think a factor of complexity in this regard. So here, for example, in that work, visually we see that there's a detection of the staircase or of the door, but we don't have exactly the limits of the door. And when we speak about interactions of humans, then it would become even more complicated. So yeah, that's my perspectives on that.
Okay. I would like to go back to the digital twin because you already asked about it. So we didn't say a lot about digital twin in your presentation. We didn't say a lot about the complexity in general. Here I would like to know a bit more. I see digital twins as a glorified environment model, which are fed real time with all the information you can capture, and which is integrated into a living model of the world. So, of course, you can demand this with things like Newton laws, kind of things to make interactive, things you don't even observe, like the ball, the ball that falls behind the desk, and the digital twin would get that once you disappear, it's very comfortable. Can you be a bit more specific in what you intend to do, where you intend to contribute, even though I understand that with the base work you made on 3D mapping, object definition, plan, and so on, these are pieces needed for building a digital twin. Can you elaborate a bit more, please?
Yes. So, as you said, for simple models or systems, it can be relatively straightforward to say that, okay, this is the digital twin, it has good performance, it predicts consistently what we expect. But when we start to be interested in robots, for example, or groups of robots that interact with nature, let's say with unpredictable external sources, then I think we can only contribute to only a small dimension of the digital twin, unless we speak of a very, very big project with multiple partners, each individual partner doing working a particular aspect of the digital twin. So when I speak of digital twins, for example, that could be used as training environments. I was thinking, for example, to go to an arbitrary area, to go to an arbitrary building, reconstruct the environment using structure for motion or a SLAM system, identify objects within, and somehow at the end have a hierarchical representation of that scene. That could be rearranged at will. So rearrange the placement of the objects, rearrange, for example, the lighting conditions, generate different, let's say, layouts of that environment, and use this digital twin as a means, for example, to learn end-to-end navigation for a robot in that particular environment. Another idea would be to so I see digital twin as a reverse engineering, let's say, approach, where we see something that is there and we try to reconstitute it in the best possible degree of detail, and to use that in the sequel as something that it allows us to do more experiments for testing or for training in a virtual environment. So there we can also see the application of generative, for example, adversarial networks that would be able to capture a particular, let's say, style for the setting of the environment, to change that style and create a new environment. So these are things that are currently that are currently being explored, and I think there is no consensus, strict consensus. There are some, let's say, norms that start to be produced by, let's say, mostly by industrial actors, but in scientific community, I think it's not quite clear, and it can mean many things. So that is going back to what I said earlier. This is how I conceive the digital twin and what I would like to do. And one particular example of that I already spoke of was in the work of Andrei Mityakov, when I spoke of the generation of different environments that could be fed to a reinforcement learning approach to train a robot to traverse staircases, to navigate indoors. So this could be a digital twin of a training, let's say, arena used for robots.
Okay. Okay, but I think it's a field, as you say, it's quite open field. That opens numerous perspectives according to your viewpoint. That question, because you say the word in your answer, you say the word end-to-end learning.
Yeah.
And you first is there is a line, which is synergy, semicolon, planning versus end-to-end learning.
Yeah.
Well, first, I mean, the synergy on one hand and versus on the other hand is a bit weird. My question is, I don't believe in end-to-end learning for complex tasks. Do you?
Sorry, I didn't hear your last phrase. You do not what?
Sorry. So my question is, so I really don't believe in the future end-to-end learning for really complex tasks.
Yeah.
Do you?
Yeah. So first of all, I how to say, I accept that I mixed the terms, and I should have put in the place of versus. I should have put planning together with end-to-end learning and not versus, because there's no, let's say, things to contradict. So that's my answer to the first part. And then the way by which I envision synergy between planning and end-to-end navigation is to have end-to-end navigation for relatively constrained horizons, spatial and time horizons, okay? Because when we speak about end-to-end navigation, this implies that we have trained an agent to navigate, avoiding collisions, for example, or for finding something. But this will always have the question that what is the guarantee that it will work in a new environment correctly? So, if we want to envision to provide such robots to an end user without guarantees, of course, it will not work. So I think planning needs to be able to control from a higher perspective, from a higher level, to have, let's say, a general path, a higher level path of things to do, okay, of steps. And these individual steps then could be assured by end-to-end policies. So, for example, an end-to-end policy could be, for example, be developed about moving a particular flipper, or moving the arm to touch something or to avoid something. So mostly something reactive, I would say, and less something to be deployed in longer special temporal horizons. So this is the way that I see that. The difficulty is to be able to master all the individual components of this paradigm. And this implies that one has good grasp of the underlying mathematical notions and the machine learning notions. And most of the time, these two paradigms are not explored, are not, let's say, deployed together. But I think this is where we are heading for, seeing recent developments in this field. So I believe in the use of end-to-end, not as standalone, but together with plan. Because if we would just rely on planning, we cannot plan everything. We cannot contain all possibilities in a graph, and also it is a task that has a certain computational cost. So I think we need the optimal is to balance, to have some sort of switching, some sort of alternation between the two, depending on the context.
Okay, thanks. Thank you, Sandra. So I will leave the microphone because I think it's been too long. Thank you very much, Javier.
Thank you, Simon, for your comments and your constructive feedback as well.
Tomas, SVOBODA.
Please, Tomas, the floor, you can pose your questions.
Okay. So difficult for me because I just witnessed, my questions have been taken one by one, so not many left for me. If I can rephrase, I definitely admire your effort during your career to keep a kind of coherent research story for yourself, because I can definitely imagine that it's not always easy when working on different projects to keep focus on the main goal. So this is definitely good. How did you manage? So concerning I wanted to ask about the future research program you put it on the slide. It's sort of clear, but it still somehow feels too dispersed. So my question is, what is actually the most interesting, say, robotic element? Because robotic part of your research is the closest to my heart. So what is the current most interesting challenge in robotics for you?
So if I heard well your question, you would like me to highlight a particular, let's say, sub-theme from all these axes and sub-themes.
So okay, I mean, currently, what is the most interesting robotic challenge for you? So what is the hope? Is it the biggest challenge for you? What is the biggest open problem in robotics? I mean autonomous robotics.
Yeah. I'll have to reflect on that. I think a handicap, or if I can term it a bottleneck in robotics, is that there is a lot of dispersion and a lot of, let's say, diversity in robotic platforms. Okay, even if there are some standard platforms that are used, let's say, internationally, but most of the, I mean, the handicap is to in robotics is to do something with one particular robot and then to do it with another robot. How to transfer what you manage to do with one robot to another one. So in terms of research, I think a terrain of that I would personally like to continue working and to invest is the capacity to transfer things, behaviors, let's say capacities, skills learned from one robot that can be exploited by another robot of not necessarily of the same, let's say, morphology or sensors. So I think here neural networks, research on neural networks is particularly helpful. So the neural network somehow allows one to put inside some black box or somehow to put many minor details in something that will allow it to be trained and will discover by itself the best, let's say, way to accomplish a task. So I'm interested to see how we can do this kind of neural network engineering in the first, the beginning of neural network, in the middle, and at the end, so as to have a more easier transfer of behaviors from one setting, one robot to another one. So that is the first topic that I think has a lot of, I mean, it's already giving, let's say, liberating, allowing to advance research in robotics. I think another one concerns now our capacity nowadays to have to use more and more simulated environments, okay, to train, to start at least to train robots to do something and leave the last stages of training to be deployed in the real robot, where normally there is lesser risk to consider. So I don't have some. So here the topics to work could be how to generate, how to use, how to perform data augmentation, how to use a digital twin, for example, to present to an agent environments of sufficient realism or sufficient, let's say, spectrum, so that it would sufficiently cover the possibilities to be encountered in real life.
Okay, I think for me it's good enough.
Yeah, okay.
Maybe if I may say more technical one.
Yeah.
The negative obstacles, you know.
Yeah.
By chance, do you have any kind of idea how to do it better, or you know how to decide when to stop? Deciding whether the slope is getting endangered and go back into robot or to continue.
How to make it better? Well, the work that I presented, I definitely didn't go until the, let's say, was not exhaustive in accounting for all possible complexities. So ways by which I could think of making it better, I think it concerns most how to delimit a gap and less how to traverse a gap. I mean, because when a robot will have to traverse a gap, I think there is not a lot of liberty, not a lot of possibilities in doing so. The risk has to be minimized. So there would be space to improve the perceptual side, and perhaps to have to conceive a way to perceive a gap in a way that would increase certainty about what are the limits of the gap, which are the potentially less well captured areas of the gap, and so that it would be avoided. Well, yeah.
It's good enough. I mean, it was more kind of a personal question because I somehow sometimes I got the impression that robotics really are kind of more concerning about the going up the obstacle, not as much about going down. So to me, for instance, the problematics of going down and deciding the best way to descend actually.
Yeah.
Now more interesting, right?
I can elaborate a little bit more, if you allow me, on the problem of the gap detection. So there are what I would call the conventional gaps that have, let's say, limited size, but a negative obstacle also qualifies in the scenario when a robot approaches a descending staircase. So the robot would have in front of it an area without encountering obstacles, so it could be completely empty. And in that case, it's not a gap to be traversed, but it's a gap to be, that has to be carefully approached before a robot starts to descend a staircase. So that is something that we didn't have the chance to work on in the context of the thesis of Andrei. But if we had the opportunity to work on that, that is to devise, for example, a policy just for approaching the beginning of the staircase, of the descending staircase, that would make more realistic that work in that respect.
Okay, thanks. Yeah, one more question. And thank you for the presentation. I invited also the other here, the kind of cherry on top of the thesis. So I enjoyed it.
Thank you very much, Tomas, as well, for all the nice, for the good questions that you asked.
Thank you. Now, Cédric.
So, Cédric, I don't know if you...
Okay, it's my turn?
Yeah.
I cannot hear you, okay. So first of all, I would like to thank you for this invitation. It's really a great honor for me to be here with you, even if I'm a little bit disappointed because it was not possible for me to reach you to the front to that. So I'm sorry for that. Okay. You did a really great work in a few years, so congrats for that. And as Simon, Thomas, and Antonio said, you did a great work with homogeneous work. It's really important to be homogeneous in your work. And I think that proves that you are the main actor of your research, which is really important. So congrats for that. You had already a lot of questions, so it's difficult for me to ask any question, but anyway, I think maybe we can consider your contribution and your perspective according to what Simon said, too many of this learning. So I have a question about that, just from my expertise. So I would like to benefit from your expertise. First of all, you use Habilitation, and right now they integrate a lot of methods, starting from the model depth, which are able to estimate the depth only with Habilitation. Do you think that right now we are able to delay depth sensor and use only Habilitation for robot television?
Yeah, so this work that I presented, they date back to the the previous decade, let's say, middle of the previous decade, when there was the emergence of the RGBD sensors and different generations of Kinect. Nowadays, it is true that due to the abundance of training data, we can regress depth quite accurately just using RGB. Now, for most of these works, obviously the regression of depth, I mean the values of the depth are relative. So we have perhaps a good quality of the depth image, but we cannot exactly, let's say, extract the metrical scale of that. Well, okay, even if we can also try to train to regress the metric part. But I think for navigation of robots, well, yes, we could use just RGB images to avoid obstacles that are far. If they are far, the robot would be able to avoid them without colliding. But for what is near and potentially could come in collision with a robot, I think we could not just rely on RGB. We would need to have some sensor that would perform the environment in an active way, so through active sensing, or by, I don't know, stereo or something. Let's say something geometrically valid, so as to have a metric notion of the depth. So this is so it depends what we want to do, and I would extend this by saying that RGB images are also, let's say, dominating today when it comes to other tasks, such as, for example, extracting the skeleton of a human. So we have different projects. We are working in the team in some projects where we have estimated, we have compared the quality of calculating the skeleton of the human using the depth modality and the RGB modality, and the quality using RGB is way better than the depth. So yeah, I think nowadays these kind of sensors, RGBD sensors, are lesser used, but we need to know what we want to do with it.
Okay. You mentioned about 3D model, you mentioned that, which is a lot of, where we have a lot of work right now. And do you think that now is useful for robot navigation?
For robot navigation?
Could be useful for robot navigation, because I think it is time consuming, but is it possible to use it in real time and so?
Yeah, I don't want to pretend that I have the answer to that. This is a field of that is relatively recent. So speaking of neural radiance field, so I wouldn't be able to say if we can envision to use nerve for navigation, perhaps in some auxiliary or some perimetral, how to say, some task which is secondary. For example, in an active perception, let's say, environment where the robot will have to assess different possibilities to perceive something, and before doing that, it could employ a nerve to see how some object would look from another point of view before actually doing that. That could be, I could envision that. But for a reactive or a real-time use, I cannot say. I am very interested in this domain, and this is something that I would like to dwell in the subsequent projects.
Your acquisition 2019 usually work about the human model, and do you think that work is Habilitation now?
So do you speak about the works about representing the human inside the robot workspace with these density functions?
Yes.
No. Well, if it is state of the, it was state of the art, I guess, when it was published, but now it's like 10 years or so where this was published. So, as I said, this field where we have humans involved and we want to perform a research, there is a complexity of having ground truths about where is a particular interaction that's happening, when does it start, when does it end, where are the limits. So I think this is something that is still challenging today to do. And even if we manage to have a certain ground truth at a certain amount of time, when humans are so rich in their behaviors and so, let's say, unpredictable, that I think the main handicap is not the method, but more like what we consider as a ground truth. What can I say? Perhaps we could have systems that are able to socially interact with humans, not through the use of ground truth, but through the use of, let's say, models that, language models. For example, we can envision bots that are able to, that are so much extensively trained in language and interaction that are able to engage in an interaction, and we will not have to base ourselves to visual features. I'm not sure. I'm not sure I can say what is the best. Where are we heading in that respect?
About qualification, you need to work on reinforcement learning, and some researchers do initial learning. What is your opinion? Do you prefer to work on reinforcement learning or initial learning? What is the way to go?
Yeah, so there are, one has to decide this from the conception of the project. There are problems where we don't have in our disposal an expert, or expert data are very difficult to have, or are noisy. So if I have a particular, I think it's more interesting and challenging to tackle problems where there is scarcity of data. If we can employ imitation learning, then like supervised learning, there is not really much to do. On the other hand, through reinforcement learning, where things are, let's say, less supervised, and we let the exploration find the best way to do it, I think reinforcement learning can also teach us things. So we can discover ways to accomplish a task, a perception task, or a navigation task, or a control task, with ways by which humans never thought of. So in that respect, it's interesting. And in that particular project, the PhD thesis of Turkish intervention that I mentioned, it was the case. Sometimes, at least from my point of view, I saw behaviors being developed that I wouldn't have anticipated to be developed with respect to the placement of the flippers, for example. I would expect that they would be completely flat to have a maximum interaction, but the policy was not converging in that way. The policy decided differently, and it turned out that in reality it was better as well. So I think reinforcement learning, when we can deploy that, we can discover new ways, and it's more exciting.
Okay, just one more question about your perspective, because I'm still curious about that. You mentioned that you want to work on semantic segmentation. I don't know if you know the really recent work about Meta and the Facebook on called segment everything.
Yeah, I saw that. Yeah,
I had a question to you on this or that.
Sorry, I'm not sure I heard the question.
So my question is, like, what kind of contribution you're saying?
Yeah.
Before this paper about the semantic everything.
Well, this segment anything, if I recall well, this SAM approach was for images. for RGB images. Yeah. And so when I spoke of semantic segmentation, I was mostly referring to 3D point clouds, color thin point clouds. Well, okay, we can imagine that one day there will be some version 2 or version 3, like a YOLO or whatever, that will segment anything in 3D point clouds, but I think we are not yet there yet. I think in the SAM paper they had, I don't remember how many thousands or how many data they have, how many experts, how much annotation, extensive annotation they have put into this network to segment anything. I think for 3D point clouds, the amount of training would be considerably more elevated to be able to have something like this. I hope I have some time ahead of me to contribute in that field, and that there will not be the sound that will intercept my research. So I have some hope in that. Yeah. So it was about yeah.
I have to realize that I'm pessimistic because it's really, difficult to be better than data company like that.
Yeah. Yeah. On the other hand, you see, when we are feeding training data, okay, to a network to learn to segment something, then most of the times there is an implicit, let's say, guidance. How to say? So these are images that were taken, for example, by humans, okay, and already that helps training. When you have a robot that has to explore in the environment, it will not navigate as a human. It will not have the same vantage point. It will not see exactly the same things. So I think we cannot, at least at this stage, we cannot hope to have the same or very similar, let's say, training data that would be needed for a robot to segment images. There will be situations where there can be very little information for the robot. For example, no texture, or the geometry will not be sufficiently, how to say, informative. So as I said, I hope that, and I think that this is what makes robotics exciting, is that it puts computer vision really to the limits of what can be done. And as I said, it is about open set problems, and maybe we are very well performing in one particular semantic segment data set, and we attain 95% precision of segmentation, I don't know, but we know very well that when we try to deploy this to new environments, they don't generalize very well. So I think we still can hope and be a little bit optimistic that there are things to do for robots.
I hope so. Thank you for the answer, and thank you for great work. So I give you the floor.
Thank you very much, Cédric, as well, for your questions and comments. I think, yeah.
Okay. Now Cédric BUCHE will ask some questions.
All right, thank you, Vincent. Thank you, Panagiotis, for the presentation, for the invitation. Yeah, obviously it's my pleasure to be here. So you present a work of 12 years, which is it's a huge work. You are super active. You are co-leading a team, Rambo. So yeah, I think you are ready to be professor. So I'm super happy to be here, and I have a lot of questions. So first, yes, I agree with my colleagues. You provide a lot of contributions, a bunch of projects, a lot of supervision. But what maybe is missing, and maybe you can focus more, this is the common story. And in your presentation, it was quite clear. You switch from one topic to another one, and the transition is not super clear. And even between the huge milestones, which is computer vision and navigation, I think you have to make an effort to explain the link. And maybe later, try to focus on one topic. So my first question, which is very difficult, but I'm happy to ask him. If you have to choose one contribution, what is the main contribution of Panagiotis Papadakis?
That's very difficult question. If I can choose one contribution among the set that I talked, I think well, I'm not allowed to speak about the PhD thesis because it's not part of the HDR. So with respect to the later works, I think that would more likely be to the recent work in developing controllers for traversing positive and negative obstacles, so going up and down staircases. This was a problem that was partly tackled in the literature. And when I say partly, I mean that some, for example, none so far had accounted for using the entire action space, using the robot arm as well, not just the flippers, and to traverse unknown staircases. So I think that in that work allowed to show what we can gain through state-of-the-art reinforcement learning approaches, to learn something in simulation, and finally see that we can use that in a real robot, in a unknown staircase, with good results. There could be other amendments, other improvements that we could have done, for example, to not rely to the external markers that were used to have the position of the robot or the staircase, but I deemed that this was of secondary interest, and we could have quite straightforwardly have a robot localization or stairways localization through the sensor of the robots. So I think, if I would highlight something that I'm particularly proud, perhaps because it is more recent and I remember better compared to my previous works, that I would highlight this one.
Okay. So next question. So you explained that one main application is assistive robotics. So when we have assistive robotics, we have human in the loop. And the idea is to have interaction between the human and the robot. It can be help, it can be collaboration, competition, whatever.
Yeah.
Can you highlight in your work in which way you tackle this interaction between human and robots? Not only perception of human activities, which can be done by camera, not a robot, but more an interaction, like to be active, to do something, because it's interesting from assistive point of view.
Yeah, this is something that is relatively overlooked compared to my existing works. So I could explain that to the fact that this was not the subject of my work before joining INT Atlantique. So I worked in projects where the concern was different. And speaking of the period from when I was here in Brest, this is relatively, let's say, the capacity to do this kind of research is relatively recent. There were some projects, there are still some projects where we are supposed to invest this aspect. COVID made things a little bit complicated to do experiments between robots and humans. So this, yes, it's sure that it's something that I would like to work more in my future works. So I hope we will be able to work on that. So if the question is which particular theme I would have liked to work in that respect, I don't know, is it a question?
Yes.
Yeah. So inclusion of a human in the loop in assistive robotics.
I think you should speak louder.
Yeah. Can you hear me now?
Yeah.
Yeah. I was a little bit. Yeah, I have pointed the camera to Cédric. Sorry, we can't see all of us at the same time. So the theme I think that it would be interesting to explore, to include the human, would be to use data sets that capture human activities, for example, of daily living, or to do some particular task. It could be preparation of food. It could be arranging objects in an environment. It could be manipulating some device. I think there are sufficient data sets that show this from an egocentric point of view of the human while doing this, and it could be used to train a robot to know which objects are relevant to the tasks, how they have to be put next to each other. Yeah, so that could be a theme that could be of interest. Yeah, so this is something to do in my to-do list.
I think you have a huge opportunity at IMTA because there is a team which is Inuit, which is working a lot of human digital twin, and you talk about digital twin.
Yeah.
And having digital twin for robots is nice, but digital twin for robots plus human, that means mixing your real human, real robots, fake robots, fake human. That's something that is very interesting, and I think you have a huge opportunity because those guys are top level.
May I say one last phrase in this question?
Yeah.
So, as I agree that this is something worthy of exploration, this is something that, let's say, at the level of the team, of Rambo team, we want to explore, and this is why we have we look for a new member of the team to join the team as a professor that has this particular expertise.
Yeah.
So this is something that we definitely want to work, and something that would raise the team higher to where it is. Yeah.
Actually, it was my last question.
Okay.
As you are leading a team, you are going to be professor, I guess. Yeah. What can leverage the activity of the team?
So
what can be the top priority to put the team at international level?
That's a very good question. Well, I think the team is already in top level. We have done interesting things, and we have accomplished tasks of international, let's say, reputation. And judging from, let's say, who we are, how many we are, and where we came from, I think we have a good standing in my eyes. If I would be continuing to represent the team and sketching a path to follow, I don't want to I don't want to say it would be this and this. I think that it's something that will have to be discussed collectively. I think we know who we are and what are the strong points and less strong points. I think we need to, well, globally speaking, as I said, I think in one of the questions of who was it? I think somebody asked me a question, but I don't remember who. And I spoke about the capacity to explode things that are learned from our robot and that can be exploded by another robot. We have multiple platforms in the team. The ambition was to be able to cover different use cases, but this is, from one point of view, let's say, this gives an added value to the team, but it can also be a handicap because it supposes, as I said, that there is a significant workforce just to support this kind of experiments. So I think we need to invest more on works that are exploitable in multiple robots at a time. We need to abstract, be it for vision, be it for mobility, be it for manipulation, be it whatever. We need to, by design of our project, to have this approach that can be abstracted so as to be able to have the less overhead possible when we want to test with a real robot. Working with a real robot can be very technically demanding. So, and if we have to change and go to another robot, it's as you know very well, it can be a real bottleneck. So I think, yeah, and in that sense, we need to. I think we have an interest in doing more fundamental, a little bit more fundamental research and less technical, because we are able. We can demonstrate that we have a very good technological know-how of making robots to work. Perhaps one part of the team, it's open to discussion, could be just dedicating to this aspect of making things work and be able to master the low level, and another part of the team that would be most interested in pushing the theoretical side, but not individually, one working separately from another. But yeah, I think we need to better control, let's say, to have a strategy on that.
Thank you, Panagiotis. I have to say you did a very good job for the team. So just continue like that and it will be perfect.
Okay, thank you very much, Cédric.
Thank you, Cédric. Now I will ask you one or two questions. Firstly, I would like to thank you a lot to invite me to your HDR conference. Your document is very clear, and you point out the problem you address and the solution, the appropriate solution you give. This is a synthetic and effective document. During the drink, I will give you some advice to improve it just a bit. Okay. I have one question, but I think you already answered about cooperation between robots. A part of the lab work on swarm robotics. And how do you feel your work could be used to have some robots which will be able to cooperate?
Yes. So this is a dimension that I have not really reflected on. I would mostly be inclined to do research on the complementarity of robots. Collaboration between multiple robots that are more or less have the same, let's say, locomotion or the same capacities. I think this goes beyond my interest and my background. But when it comes to collaborating with, let's say, two robots, one ground robot and an aerial robot, that could be a theme of work. The collaboration. So, in what forms could come this collaboration? Well, it depends on the use case. Depends on what kind of problems we are dealing with. I think if we speak about assistive service robots, well, I think we are a little bit far from envisioning multiple robots next to a human. I would mostly consider one at best that can contribute to one task. Perhaps definitely collaboration could come in the form of a robot and a smart environment. So these are things that we investigate in the team since some time. So it's not a robot with another robot, it's an ambient intelligence with another robot. The ambient intelligent environment is something that has a global, omnipresent understanding of the environment, whereas on the other hand, the robot can go on demand, focus the attention on one particular area. So these are things that we have explored and we explore in the integration of smart environments with robots. So this is about companion robots. For projects that are ongoing and perhaps they will be later more projects of this kind related to urban search and rescue, then there is definitely a vein, let's say, of research that could be dedicated to collaboration between, for example, a ground robot, an aerial robot, or a limbed robot that, for example, a little dog that is going to climb stairs. But these are more like applications of industrial scale, let's say, and less applications where we will have a single user that would be interested to use this robot. So these like defense applications, civil applications, industrial applications, where we can speak of robot-to-robot collaboration. Currently, I think in the team we are not really into this prospect. We are not doing research in that, or very little. So that's what I could say.
Okay, thank you for